The laws of physics might not be permanent fixtures of reality. We are venturing beyond our horizons to explore new interpretations of cosmic evolution. Our journey will take you through theories that dismantle everything you thought you knew about the universe, from its fiery birth to its ultimate fate. By the end, your understanding of reality will be fundamentally reshaped. We will confront a universe that may have no beginning, where dark energy decays and time itself is an illusion. How do you picture our place in a cosmos that is stranger than we ever imagined? Our universe may have no true beginning at all. The moment we call the Big Bang might not be a singular creation event, but a transition, a cosmic turning point. Think of it not as a bang, but as a bounce. A previous universe, having expanded to its limit, could have collapsed back in on itself, only to rebound into the expansion we observe today. This is the heart of the Big Bounce theory, a radical alternative to a singular beginning. It suggests our cosmos is part of an endless, cyclical dance of contraction and expansion. This idea emerges from the frontiers of quantum gravity, where the extreme laws of the very small meet the grand scale of the cosmos. At these incredible densities, gravity may have acted as a repulsive force, preventing a true singularity and instead initiating a rebound. This process could erase nearly all information from the previous cycle, yet subtle quantum fluctuations might survive, imprinted like cosmic memories onto the new universe. Physicist Roger Penrose takes this concept even further with his conformal cyclic cosmology. He proposes a universe of endless eons, where the distant, heat-dead future of one cosmos becomes the low-energy, uniform starting point of the next. In this model, our universe is a phoenix, eternally rising from its own ashes. To visualize this, picture a rubber band. You can stretch it out to a vast size, representing the expansion of a universe. Then you can let it contract back to a tiny, dense state. Now, imagine that process repeating forever. This cyclical nature challenges our most fundamental experience, the arrow of time. If the universe has no start and no end, then what is time really? Is it just a local phenomenon, a property that emerges within each cycle, only to reset when the next bounce occurs? These are not just philosophical questions. Scientists search for observational evidence, like the faint whisper of primordial gravitational waves. These ripples in spacetime, if detected, could carry the signature of a pre-Big Bang era. The BICEP2 telescope, for instance, scans the cosmic microwave background for a specific pattern, a curling polarization that could be the ghostly imprint of those first moments. While the data remains inconclusive, the hunt itself forces us to reconsider everything. If our universe is just one chapter in an infinite story, then the very fabric of reality is far more dynamic and mysterious than we ever dreamed. This boundless cycle of cosmic rebirth is not the only idea challenging our origins. The very mechanism thought to have shaped our universe, cosmic inflation, is itself being reimagined. The standard story tells of a brief, monstrously fast expansion that smoothed and stretched the infant cosmos. But what if that event was not a single, uniform blast, but a chaotic and eternal process? This is the heart of eternal inflation, a theory suggesting our entire observable universe is just one bubble in a vast, frothing cosmic ocean. Pioneers like Alan Guth and Andre Linde envisioned inflation not as a one-time event, but as a driving force that never truly stops. In this picture, the fabric of spacetime is constantly boiling with energy, a state driven by what physicists call a scalar field. Think of a vast, rolling landscape of hills and valleys, where each valley represents a stable state of reality. Our universe exists in one such low-energy valley, but through a process akin to quantum tunneling, random fluctuations can kick a patch of spacetime over a hill, allowing it to rapidly inflate and form a new bubble universe. This process is endless, creating a multiverse, an infinite foam of pocket universes, each with its own unique properties. Andre Linde described this as a chaotic, self-reproducing process, where each new bubble can itself become a seed for more inflation, forever generating new cosmic domains. The implications are staggering. In this eternal churn, the fundamental constants of nature, like the strength of gravity or the mass of an electron, could be set to different values in each bubble. Some universes might be stillborn, collapsing instantly. Others could be sterile, unable to form atoms or stars. We simply happen to live in one where the numbers allow for galaxies, planets, and life. A powerful analogy is a giant pot of boiling water. The roiling water represents the energetic, inflating background. Bubbles constantly form, grow, and sometimes collide. Each bubble is a separate universe budding off from the eternal whole. This idea is not without its clues. Our own cosmic microwave background, the afterglow of the Big Bang, shows subtle anomalies, large-scale patterns that are unexpectedly cold or uneven. Some researchers speculate these could be bruises, the imprint of our bubble universe colliding with another in the distant past. Yet the greatest challenge for the multiverse is testability. How do we prove the existence of realities forever beyond our observational reach? This pushes cosmology to its limits, forcing us to ask if some truths are fundamentally unknowable. If our cosmos is just one fragile bubble in an infinite froth, then the nature of reality is far stranger and more vast than we ever dared to believe. The mystery of dark matter only deepens as we look closer. For decades, the leading candidate was the WIMP, a weakly interacting massive particle, a heavy ghost that would reveal itself only in the most sensitive detectors. Yet after years of searching, these particles have not appeared. This failure has forced a profound shift in thinking. What if dark matter is not one thing, but many? Theorists are now exploring a whole zoo of possibilities, from particles trillions of times lighter than an electron to primordial black holes forged in the universe's first second. Consider the action. This hypothetical particle was conceived to solve a different puzzle in particle physics, but it perfectly fits the profile of a dark matter candidate. It is incredibly light and feebly interacting, a wisp of a thing that could pervade the cosmos in vast numbers. In one compelling model, actions would behave not as discrete particles, but as a coherent wave oscillating throughout space, a concept known as fuzzy dark matter. This wave-like nature could explain why small dwarf galaxies have fewer dark matter halos than expected. The wave's wavelength is simply too large to fit inside them. Another radical idea comes from physicist Lisa Randall, who proposes that dark matter may reside in a hidden dimension, a parallel reality that overlaps our own. In this model, dark matter feels a force entirely its own, allowing it to interact with itself through a kind of dark light or dark electromagnetism. This self-interacting dark matter could solve a glaring puzzle. Astronomers have discovered a handful of galaxies that appear to be completely devoid of dark matter. If dark matter can collide and scatter, it could have been stripped away from these galaxies during ancient cosmic encounters, leaving behind only visible stars. The evidence for dark matter's existence remains as solid as Vera Rubin's foundational work, which showed galaxies spinning so fast they should fly apart without the gravitational glue of unseen mass. The question is no longer if dark matter exists, but what it is. deep underground in abandoned gold mines, experiments like LUXZEP-LIN sit in profound silence, waiting for the faintest shudder of a dark particle collision. Soon, the LISA mission will listen for the gravitational hum of primordial black holes, ancient relics that could constitute the missing mass. All these ideas point toward a dark sector, a hidden universe of particles and forces operating alongside our own, interacting with us only through gravity. This is not a single mystery but a web of them. If dark matter can interact with itself, if it can be pushed and pulled by its own hidden forces, then our entire cosmic map is missing an entire dimension of reality. And this leads us directly to its even more enigmatic partner, the force that is not pulling the universe together, but relentlessly tearing it apart. The force accelerating our universe's expansion might be slowly fading away. For decades, the simplest explanation was Einstein's cosmological constant, a fixed energy woven into the fabric of empty space itself. But what if this dark energy is not constant at all? A new class of theories suggests it is a dynamic entity, a cosmic field that physicists call quintessence. Unlike a static constant, quintessence can evolve over time, its strength either diminishing or growing as the universe ages. This idea was propelled into the mainstream by the work of astronomers like Adam Rees, whose observations of distant supernova first revealed the shocking acceleration of the cosmos. That discovery pointed to an unknown energy, but its precise nature remains one of physics' greatest enigmas. The implications of a changing dark energy are profound for the ultimate fate of everything. If dark energy weakens, gravity could eventually regain dominance, pulling the universe back together in a fiery big crunch. Conversely, if it strengthens into something known as phantom energy, the outcome is far more violent. Phantom energy would cause the expansion to accelerate without limit, eventually overcoming the forces that hold galaxies, stars, and even atoms together. The universe would end in a big rip, a catastrophic tearing apart of spacetime itself. We are not just theorizing. Observational tests are actively hunting for clues. Scientists use Baryon acoustic oscillations, the fossilized imprint of sound waves from the early universe, as a giant cosmic ruler to measure how the expansion rate has changed over billions of years. They also continue to study Type Ia supernova, the same cosmic milepost that first revealed the acceleration. The data, however, is introducing a puzzle rather than a clear answer. A growing discrepancy known as the Hubble Tension reveals a conflict in how fast the universe is expanding today, depending on whether we measure it using the early cosmos or nearby stars. This tension might be the first crack in the model, a hint that our understanding of dark energy is incomplete. Theoretical physicist Sean Carroll points to the deep puzzle of vacuum energy, noting that the predicted value from quantum theory is astronomically larger than what we observe. This staggering fine-tuning problem suggests that something fundamental is missing from our picture. If dark energy is not a constant but a dynamic field, it could resolve this mystery, evolving to its current low value over cosmic history. The very fact that we can conceive of a big rip or a big crunch forces us to confront the possibility that the laws we take as permanent might be transient. What if dark energy's behavior is a signal, not just of a new particle or field, but of new laws of gravity itself? This question strikes at the foundation of Einstein's general relativity and propels us toward the next great mystery. Einstein's theory of gravity is a masterpiece, but what if it is not the final word? For decades, the cosmic mysteries of dark matter and dark energy have been explained by adding invisible ingredients to the universe. Yet a radical alternative suggests we need not invent new forms of matter or energy, but instead rewrite the laws of gravity itself. This is the core of modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom, MND starts with a simple but profound idea. The force of gravity may not weaken with distance in the straightforward way Newton and Einstein described. At extremely low accelerations, like those found in the faint outskirts of galaxies, gravity could experience a boost. This single modification perfectly accounts for the flat rotation curves of galaxies, the very observation that first pointed to dark matter. Stars orbit galaxies so quickly that visible matter alone cannot hold them. Instead of invoking a halo of dark matter, MND suggests that gravity itself is stronger in these dim regions, pulling the stars into stable, high-speed orbits. Milgrom himself stated that the evidence from galaxies is a clear signal that our understanding of gravity is breaking down. But how do you build a full theory of gravity from this premise? This led to relativistic extensions like TVS, tensor vector scalar gravity. This theory incorporates the MND idea into a framework that can compete with general relativity on cosmic scales, attempting to explain phenomena like gravitational lensing without dark matter. In general relativity, the immense gravity of a galaxy cluster bends light from distant objects, creating distorted images. This effect is attributed to the cluster's dark matter. Modified gravity theories like TVS propose that the gravitational field itself is different, creating the same lensing effects through a more complex interplay of forces. Another compelling idea is emergent gravity, which suggests that gravity is not a fundamental force, but a side effect of the quantum information stored in the fabric of space. In this view, dark matter is an illusion, a mirage created by the way we perceive the underlying structure of reality. The most significant challenge to these ideas comes from a cosmic crash site known as the Bullet Cluster. When two galaxy clusters collided, their visible gas clouds slammed together and slowed down. But maps of gravitational lensing showed that most of the mass, the source of the gravity, had sailed right through the collision, separated from the visible gas. This was hailed as direct proof of dark matter, a substance that does not interact with normal matter. Proponents of modified gravity, however, have not conceded. They propose that the equations of their theories, when applied to such a violent and complex event, could also account for the apparent separation of mass. They argue that the gravitational field in these unique conditions might not be perfectly traced by visible matter, creating a ghostly signature that mimics dark matter. The debate is far from settled. This pushes the question into the laboratory. If gravity behaves differently at tiny accelerations, could we detect it here on Earth? Extremely sensitive tabletop experiments are now searching for any deviation from Newton's familiar inverse square law at microscopic distances. Finding such a deviation would be a monumental discovery, suggesting that the laws of gravity are indeed scale-dependent. The mainstream physics community remains skeptical, pointing out that while MND works remarkably well for individual galaxies, it struggles to explain the precise observations of the cosmic microwave background or the large-scale structure of the universe without some form of dark matter. Yet the persistence of these modified gravity theories highlights a crucial and humbling possibility. Einstein's general relativity, for all its predictive power, might be a brilliant approximation, a theory that works perfectly within our local cosmic neighborhood, but cracks when applied to the vast, lonely emptiness between galaxies. This inquiry into the true nature of gravity inevitably pulls us into an even deeper mystery, into the quantum realm where space and time themselves may cease to exist. Einstein's smooth spacetime continuum shatters when we approach the quantum realm. At this deepest level, reality may be woven from indivisible threads, a granular structure where the very concepts of space and time lose their meaning. This is the domain of quantum gravity, the long-sought unification of general relativity with quantum mechanics. Two towering frameworks attempt this monumental task: loop quantum gravity and string theory, each offering a radically different vision of reality's foundation. Loop quantum gravity, championed by physicists like Carlo Rovelli, proposes that space itself is not a continuous backdrop but a fabric woven from tiny, one-dimensional loops. These loops connect to form a network of relationships, a spin network, which evolves over time to create the four-dimensional spacetime we experience. Rovelli emphasizes a profoundly relational view, where space and time are not fundamental but emerge from the interactions between quantum events. There is no where or when outside this web of connections. Picture a vast cosmic tapestry. From a distance, the fabric appears smooth and unbroken, but up close you see it is composed of countless individual, interwoven threads. The tapestry is space-time, and the threads are those fundamental loops of quantum gravity. String theory, by contrast, proposes a different kind of fundament. It suggests that the most basic constituents of reality are not point-like particles but incredibly tiny, vibrating strings. The specific resonance of each string determines whether it manifests as an electron, a photon, or a graviton, the hypothetical particle of gravity. This elegant idea, however, demands extra spatial dimensions for its mathematical consistency. Our familiar three dimensions of space and one of time may be just a visible slice of a richer, higher dimensional reality. These hidden dimensions could be compactified, curled up into shapes too small for us to perceive. Edward Witten's exploration of string theory revealed a staggering consequence known as the landscape, a vast collection of possible solutions, each corresponding to a universe with different physical laws and constants. Our cosmos, with its specific properties allowing for our existence, would be just one possibility in an almost infinite cosmic catalog. In this framework, our universe might be a three-dimensional brain, short for membrane, floating within a higher dimensional bulk. The collision of two such brains could have been the event we call the Big Bang. This introduces a profound concept, the holographic principle. It suggests that all the information describing a volume of space can be encoded on its lower dimensional boundary, much like a three-dimensional image is stored on a flat, two-dimensional hologram. Our reality, in essence, might be a projection, a cosmic illusion generated by quantum bits of information living on the distant horizon of the observable universe. These theories force us to confront the problem of time. In the equations of general relativity, time is a dynamic player. In the standard equations of quantum mechanics, it is an external, absolute parameter. But in a theory of quantum gravity, time, as we know it, may not exist at all. It could be an emergent property, a collective illusion generated by the changing relationships between quantum events. How can we possibly test such ethereal ideas? The remnants of the universe's birth may hold the key. The faint primordial gravitational waves that ripple through the cosmos could carry an imprint of these quantum gravitational effects from the first moments after the Big Bang. Future observatories like the space-based LIS mission might one day detect these whispers, offering a glimpse into the quantum structure of spacetime. Nowhere is the conflict between quantum mechanics and gravity more acute than inside a black hole. According to general relativity, an astronaut crossing the event horizon would notice nothing special, at least initially. But quantum mechanics insists that information cannot be destroyed. This leads to the black hole firewall paradox. Does a searing wall of energy, a firewall, incinerate anything falling into a black hole to preserve information laws? Or is our understanding of either quantum theory or gravity fundamentally flawed at this precipice? Quantizing gravity completely rewrites the story of cosmic evolution. It suggests that the Big Bang was not a true singularity, but a quantum bounce from a previous cosmic phase. It implies that the smooth expansion of the universe emerged from a foaming, discrete quantum geometry. If spacetime itself is quantized, then our entire history, from the first instant to the distant future, is built upon a foundation more alien and wondrous than the continuous fabric we perceive. The smooth river of time we experience may be a powerful illusion. Physics at its deepest level suggests that time, as a fundamental arrow, might not exist at all. What we perceive as the relentless forward march could be an emergent property, a side effect of something more basic. The classical story tells us time began at the Big Bang, but what if that singularity was merely a point where our concept of time broke down, not where it started? Julian Barber offers a radical perspective, arguing that time is not a flowing river but a measurement of change. There is no river, only the landscape through which it appears to flow. Each moment or now is a complete configuration of the entire universe, and our sense of passage is just our consciousness moving from one now to the next. This view dissolves the idea of a beginning entirely. How then do we model a universe without a starting edge? James Hartle and Stephen Hawking proposed their famous no-boundary proposal. Imagine the history of the universe not as a cone starting from a sharp point, but as a smooth sphere like the surface of the Earth. The Big Bang would be analogous to the South Pole. There is nothing south of the South Pole, no edge, no boundary, and no singularity. It is simply a point on a closed surface. In this model, time blends seamlessly into space as we approach the beginning, avoiding the mathematical infinity that plagues the standard Big Bang picture. Another approach, causal set theory, builds reality from the ground up. Picture a vast, growing network of points. Each point represents a fundamental event, and the links between them represent cause and effect. Spacetime and its smooth, continuous geometry are not primary. They are a large-scale approximation, an emergent smoothness from this discrete, shimmering web of causal connections. In this view, time is the sequence of these events being added to the network. But where does our powerful sense of a directional arrow come from? This is where the second law of thermodynamics enters. The universe began in a state of incredibly low entropy, a state of high order. The arrow of time we feel, the reason we remember the past and not the future, is the direct result of the universe evolving from that ordered state toward ever greater disorder. Our conscious experience is tied to this cosmic increase in randomness. This leads to the block universe concept, where past, present, and future all exist eternally in a static four-dimensional block. Your birth, your life, and the ultimate fate of the cosmos are all equally real, fixed in the cosmic structure. The feeling of a moving now is just a subjective perspective, a flashlight beam scanning across this frozen landscape. How could we ever test such an abstract idea? Scientists are proposing experiments with quantum clocks. By entangling two tiny clocks and observing how their timekeeping becomes correlated, we might detect the subtle ways that time itself emerges from quantum relationships. These are tabletop probes into the fundamental nature of reality. Now try to contemplate a universe without time. No before, no after, just a single, timeless configuration of all things. In such a reality, the very word evolution loses its meaning. There is no history to unfold, no story to tell. This stark picture forces us to confront the puzzle of initial conditions with entirely new eyes. Why did our particular timeless configuration have the potential to generate the vivid, flowing illusion of time? complete with a low entropy beginning that set the entire cosmic drama in motion. If time is not fundamental, then the origin of our universe was not a moment in time, but a transition into time. The first chapter of cosmic history was written not on the parchment of time, but on something deeper and far more mysterious, a foundational layer where the very concepts of cause and effect were born. Our universe appears to be a stunningly lucky winner in a cosmic lottery. The fundamental numbers that govern reality, the strength of gravity, the mass of an electron, the energy of empty space, all seem perfectly balanced on a knife's edge. If any of these constants were even slightly different, our universe would be a lifeless void. This is the fine-tuning problem, and it demands an explanation. Consider the cosmological constant, the value of dark energy. Quantum theory predicts it should be astronomically larger than what we observe, by a factor of 1 followed by 120 zeros. If it were just a little bit bigger, the universe would have blown itself apart before stars could form. A little smaller, and it would have collapsed back on itself long ago. The strong nuclear force which binds atomic nuclei is also exquisitely tuned. If it were just a few % stronger, all the hydrogen in the early universe would have fused into helium, leaving no water or fuel for stars. If it were weaker, complex elements necessary for planets and life would never have formed. This incredible precision points toward two radically different conclusions. The first is the multiverse. In an eternally inflating cosmos, every possible set of physical constants is realized in some bubble universe. We, of course, find ourselves in one of the rare bubbles where the numbers allow for our existence. This is the Anthropic Principle in action. Physicist Leonard Susskind, exploring the string theory landscape, argues that our universe is just one possibility in a vast, perhaps infinite, ensemble. In this view, there is no deeper reason for the values we see. We are simply here because we can be. The alternative is that a deeper, yet unknown physical law uniquely determines these constants. There is no lottery, only a single, elegant solution to the equations of reality. Philosopher Paul Davies has pondered whether a kind of life principle might be woven into the fabric of physical law, a teleological pull toward complexity and consciousness. The debate often hinges on falsifiability. How can we ever prove the existence of other universes we can never observe? Proponents point to the Higgs boson as a case study. Its mass is also curiously fine-tuned, a puzzle known as the hierarchy problem. Its discovery at the Large Hadron Collider confirmed its existence, but its precise, seemingly unnatural value has fueled ongoing searches for new physics, like supersymmetry, that would make its mass more logically inevitable. This search for naturalness is a driving force in physics. Bayesian reasoning enters the fray, with scientists weighing the probability of our universe given a multiverse versus the probability given a single, unique universe. Is the multiverse an elegant explanation for fine-tuning, or is it a philosophical surrender, a way to avoid seeking a deeper truth? The answer may redefine our place in the cosmos. Are we the improbable winners of a random draw, or is the universe in some profound sense meant for us? This question inevitably draws consciousness into the heart of cosmology, suggesting that the observer and the observed are inextricably linked in the story of everything. The fine-tuning of our cosmos points toward an unsettling possibility. Perhaps the universe is not a pre-written script, but a story being written as it unfolds, with conscious observers as its co-authors. This idea ventures into the most controversial territory of all, questioning whether reality possesses an independent existence at all. The roots of this notion lie in the bizarre world of quantum mechanics. In the famous double-slit experiment, a single electron fired at a barrier with two slits behaves as a wave, passing through both openings and creating an interference pattern. Yet, the moment we place a detector to see which slit it goes through, the electron behaves like a single particle. The very act of observation, of measurement, seems to collapse a haze of possibilities into a single, definite reality. This is the measurement problem, the central mystery of quantum theory. Where does this collapse occur? Is it the physical interaction with the detector, or does it require a conscious mind to register the result? Physicist John Wheeler took this idea to its ultimate cosmic scale with his participatory anthropic principle. He suggested that we live in a participatory universe where observers are necessary to bring the cosmos into being. He famously described this as it from bit, proposing that every particle, every field, derives its existence from the answers to yes or no questions, from binary bits of information elicited by an act of observation. In this radical view, the universe only achieves concrete reality when a conscious mind perceives it. The implications for cosmology are staggering. If the universe requires observers, then its very laws and history might be shaped by our presence. This leads to a strange paradox known as the Boltzmann brain. If our universe is just a random fluctuation in an otherwise featureless void, it is statistically more likely for a single, self-aware brain to spontaneously form with false memories of a past than for an entire, ordered universe with billions of observers to come into existence. The fact that we see a coherent cosmos and are not such isolated, disembodied brains suggests our universe is not a random accident but has a deeper principle at work, perhaps one involving genuine observation. Critics, particularly materialist philosophers, argue this gives far too much weight to consciousness. They maintain that consciousness is an emergent property of complex brains, a beautiful but accidental byproduct of neural computation, not a fundamental force in physics. They see the introduction of consciousness into quantum mechanics as a category error, a confusion between the map and the territory. Yet the puzzle deepens when we apply quantum principles to the entire cosmos. In quantum cosmology, the universe is described by a wave function, a mathematical object that encapsulates all possible histories and states. What or who could possibly perform the measurement to collapse the wave function of the entire universe? Some theorists propose the universe is its own observer, a self-excited circuit where the cosmos becomes aware of itself through the life within it. This is the hard problem of consciousness, the question of how subjective experience arises from mere matter. If consciousness is indeed fundamental, not emergent, then the cosmos might be a vast, self-aware system. We are not just living in the universe, we are the universe becoming conscious of itself, our observations the means by which it defines its own reality. This is the most profound speculative leap, one that blurs the line between the observer and the observed. While this idea remains at the fringes of science, it forces us to confront the nature of our own role in the cosmic story. Are we passive witnesses to a grand, independent spectacle, or are we active participants in its very creation? The search for an answer compels us to look not just at the abstract quantum realm, but at the largest and most concrete structures the universe has ever built. This cosmic web is the largest structure we have ever mapped, a sprawling architecture of light and shadow on a scale that defies human comprehension. Far from a random scattering of galaxies, our universe is organized into a delicate lattice. Brilliant clusters of thousands of galaxies are strung along invisible threads of dark matter, forming filaments that stretch for hundreds of millions of light years. These filaments intersect at dense nodes, the great cities of the cosmos, and between them lie the voids, unimaginably vast regions of near emptiness, cosmic deserts that can span hundreds of millions of light years across. This is not what scientists expected from a universe that began in a hot, dense, and nearly uniform state. How did such intricate structure emerge from such smooth beginnings? The answer lies in the relentless pull of gravity acting over billions of years. Tiny quantum fluctuations from the universe's first moments, imprinted as faint ripples in the cosmic microwave background, were the seeds. Regions that were ever so slightly denser than their surroundings had a bit more gravitational pull. Over eons, they drew in more and more matter from the less dense regions around them. This process, known as gravitational instability, is what sculpted the cosmos. The dark matter formed the invisible skeleton first, its gravity creating a scaffolding upon which normal matter could later condense and ignite into stars and galaxies. We can actually hear an echo of this process. Baryon acoustic oscillations are the fossilized imprint of sound waves that rippled through the hot plasma of the infant universe. These waves created a preferred scale, a standard ruler etched into the cosmos. By measuring the distribution of galaxies today, surveys like the Sloan Digital Sky Survey and the new Euclid Space Telescope can see this same scale repeated in the cosmic web. It is as if we are finding the faint, ghostly fingerprint of the universe's first second, preserved in the spacing of galaxies billions of years later. Cosmologist J. Richard Gott described the universe's topology as sponge-like. The galaxies and clusters are the solid material of the sponge, and the voids are the empty pockets. This is a crucial insight. The universe is not a random collection of things, but a single, interconnected structure where the empty spaces are just as important as the full ones. The evolution of these voids is profoundly shaped by dark energy. As the universe expands, the gravitational pull of matter tries to slow the growth of these empty regions, while dark energy's repulsive push accelerates their expansion. In our current era, dark energy is winning, causing the voids to grow ever larger and emptier, stretching the cosmic web itself. This grand structure also highlights a puzzle closer to home, the missing satellite problem. Our best computer simulations of cosmic evolution, like the landmark Millennium Run, predict that our Milky Way galaxy should be surrounded by hundreds of small satellite galaxies. Yet we observe only a few dozen. Where are the rest? This could mean that our understanding of how galaxies form in small halos of dark matter is incomplete, or perhaps that many of these tiny dark matter clumps never manage to attract enough gas to light up as visible galaxies. They are there, but dark. The very existence of the cosmic web is a direct message from the primordial universe, telling us about the nature of those initial fluctuations. Its specific geometry, the thickness of its filaments, and the sheer size of its voids is a severe test for any theory of cosmic origins. Why did the universe choose this particular pattern, this specific sponge-like form? This intricate architecture, born from minuscule seeds, ultimately points back to a deeper and more profound mystery, the astonishing uniformity from which it all began. The universe's deep past presents a paradox of perfect smoothness. Look in opposite directions of the sky, and you will find the cosmic microwave background, the remnant heat from the Big Bang, is almost exactly the same temperature everywhere. This seems logical until you realize those distant regions have been flying apart for billions of years. According to the standard laws of physics, they have never been close enough to exchange heat or information. They are like two strangers on different continents who have never met, yet are wearing identical clothes down to the smallest thread. This is the horizon problem. How can the universe be so uniform if its parts were never in touch? The leading solution for decades has been cosmic inflation, a brief period of faster-than-light expansion in the universe's first fraction of a second. This theory suggests the entire observable universe was once a tiny, connected patch that was stretched to colossal size, smoothing out all wrinkles and locking in a uniform temperature. It is a powerful and elegant idea, but the cosmic microwave background is not perfectly smooth. It holds strange, stubborn anomalies that refuse to go away. The Planck space mission, which produced our most detailed map of this ancient light, revealed a large, inexplicably cold region known as the cold spot. It is a vast area of the sky that is significantly cooler than the average, a feature that is incredibly unlikely in a simple inflationary universe. Planck scientists have openly stated that some of these anomalies, while not yet conclusive, have a statistical significance that is hard to ignore. They challenge the assumption that our universe is isotropic, or the same in all directions. Another puzzling feature is the alignment of the low-order multipoles. In simpler terms, the largest patterns of hot and cold spots in the cosmic microwave background are not randomly oriented. The quadrupole and octupole moments, which describe the universe's biggest ripples, appear strangely aligned with each other and with the ecliptic plane of our own solar system. This strange correlation has been nicknamed the axis of evil because if it is real, it suggests a fundamental flaw in our cosmological model, perhaps even a hint that our local space-time geometry is special. How could the entire universe know about the orientation of our little solar system? These anomalies have forced physicists to reconsider inflation's legacy. Could they be scars from a pre-inflationary era, imprints from a time before the rapid expansion began? Or do they point to a cosmos with a non-trivial topology, a finite universe that is folded in on itself in a way that allows for connections we cannot directly see? Alternatives to standard inflation have emerged. Some theorists propose that the speed of light was much higher in the early universe, allowing distant regions to communicate and thermalize. Others look back to cyclical models like the Big Bounce, where the universe's previous contraction phase created the uniformity we see. The data from both the WMAP and Planck missions has created a persistent tension. The standard model of cosmology fits the data beautifully, except for these few stubborn outliers. Do we ignore them as statistical flukes, or do we follow them as clues to a deeper truth? The cold spot, for instance, could be a cosmic texture, a defect in the fabric of space-time, or even the imprint of a collision with another universe in the multiverse. These features in the oldest light we can see suggest that our universe may be far more complex, and perhaps even finite, a vast but closed structure with a geometry we are only beginning to perceive. Our universe might have a hidden shape, a geometry written into the fabric of space itself. We have mapped the stars and the cosmic web, but we still do not know the most basic thing about our home, whether it is finite or infinite. The answer depends on the universe's overall geometry, which comes in three possible forms. If space is flat, like an endless sheet of paper, the universe is likely infinite. If space is positively curved, like the surface of a sphere, the universe could be finite but unbounded, with no edge. Sail in one direction on a sphere, and you eventually return to your starting point without ever hitting a wall. If space is negatively curved like a saddle, it would be infinite and expanding forever. The density of matter and energy in the cosmos determines which of these shapes is ours. This critical value is called omega. If omega equals exactly 1, space is flat. Measurements from the cosmic microwave background strongly suggest we live in a flat universe, which seems to point toward infinity. But this is where topology enters the story, a more subtle concept than geometry. Geometry is about local shape, like the curvature of a piece of paper. Topology is about global connectivity, like whether that paper is a flat sheet or rolled into a cylinder. Even if the universe is geometrically flat, its topology could be multiply connected, meaning it wraps around on itself in a finite volume. Think of a classic video game world where a spaceship flying off the right side of the screen instantly reappears on the left. The screen is finite, but there is no edge. Our universe could be like that, but in 3 dimensions. One of the most beautiful proposals for a finite cosmos is the Poincare dodecahedral space. In this model, the universe is a finite sphere whose surface is tiled by 12 curved pentagonal faces. If you could travel in a straight line, you would eventually loop back to your starting point, but the space would be so vast you would see the same galaxy in different directions, like a hall of mirrors on a cosmic scale. These duplicate images are called ghost images or cosmic crystallography. Astrophysicist Jean-Pierre Luminet has championed this idea, suggesting that the specific pattern of fluctuations in the cosmic microwave background could reveal this dodecahedral topology. The Planck satellite data has placed tight constraints on such models, and so far no clear ghost images have been found. The universe appears to be simply connected, meaning if it is finite, it is far larger than the volume we can observe. Yet the question remains haunting. If the universe is finite, what lies beyond its horizon? The answer might be nothing, but not empty space. True nothingness, a complete absence of space, time, and physical laws, is a concept our minds cannot truly grasp. There would be no beyond because the container itself would end. This forces us to confront the ultimate nature of reality, a cosmos that is all there is, a self-contained entity whose very existence may be its own reason for being. Empty space is not truly empty. It is a vibrant, dynamic arena, a quantum stage where reality performs a continuous and frantic dance. This is the quantum vacuum, a seething sea of virtual particles. According to quantum field theory, every point in space is a hub of activity, with particle-antiparticle pairs flickering into existence for unimaginably brief moments before annihilating each other. They borrow energy from the vacuum itself, existing just long enough not to violate the laws of physics. This ceaseless activity is not just theoretical. We can witness its effects in the laboratory through the Casimir effect. When 2 perfectly smooth, uncharged metal plates are placed extremely close together in a vacuum, they are pushed together by an invisible force. The reason is that the space between the plates is so narrow it restricts the kinds of virtual particles that can pop into existence. Outside the plates, a greater variety of particles can flicker, and this imbalance in quantum pressure forces the plates together. It is a direct physical manifestation of the energy of nothing. This vacuum energy, often called zero-point energy, is the leading candidate for the source of dark energy, the force accelerating the universe's expansion. It should be the cosmological constant, an energy density woven into space itself. But here we encounter what Nobel laureate Frank Wilczek has called a cosmic embarrassment. When physicists calculate the predicted energy of the quantum vacuum based on quantum theory, the number is absurdly large. It should be 1 followed by 120 zeros times greater than the value we actually observe from the acceleration of the cosmos. This is the worst prediction in the history of science, a staggering discrepancy that suggests something fundamental in our understanding is either wrong or profoundly incomplete. The mathematical process of renormalization, which successfully subtracts away infinite quantities to get finite answers in particle physics, fails completely to fix this cosmic scale problem. The vacuum energy density we see is not just a little small, it is unnaturally, inexplicably tiny. This fine-tuning is so extreme it hints at a deeper principle we have yet to uncover. One radical solution comes from string theory with its landscape of possible vacua. Our universe might reside in a metastable vacuum, a valley in the cosmic landscape that is stable for now, but not forever. This leads to a terrifying possibility: vacuum decay. A bubble of true, stable vacuum could spontaneously form somewhere in space. If this happens, the bubble would expand at the speed of light, rewriting the laws of physics as it goes. The fundamental constants we rely on, the strength of forces, the existence of atoms, would all change in an instant. This would be the ultimate end of everything, not with a bang or a rip, but with a silent, lights-out transition to a new reality where life as we know it is impossible. Experiments at the Large Hadron Collider are indirectly probing this very stability by measuring the mass of the Higgs boson, as its value is crucial for determining if our vacuum is indeed metastable or safely perched in a lasting state. Now try to contemplate a true nothing, not empty space, but an absolute void with no space, no time, and no physical laws. This conceptual challenge highlights why the quantum vacuum is so profound. It is the closest thing to nothing that physics can describe, and it is still bursting with activity. This vibrant nothingness is not a passive backdrop. It may be the engine of cosmic evolution, its subtle fluctuations potentially seeding the largest structures. How does this quantum frenzy influence the grand classical universe? One emerging connection is to cosmic magnetic fields. These vast, invisible fields thread through galaxies and galaxy clusters, and their origin is a major puzzle. Could the turbulent dynamics of the early universe, powered by the seething energy of the quantum vacuum, have generated the first magnetic seeds that later grew to shape the cosmos we see today? These vast magnetic fields are cosmic architects, shaping the universe on its grandest scales. Woven through the spaces between galaxies in a cluster like Virgo, these invisible lines of force guide the flow of hot gas and steer the paths of high-energy cosmic rays. They are everywhere we look, but their origin story is a profound mystery. How did such coherent magnetic structures, spanning millions of light-years, come to be? The answer may lie in the universe's earliest moments. One leading theory points to primordial phase transitions. As the newborn universe expanded and cooled, it underwent dramatic shifts in its fundamental state, much like water freezing into ice. These transitions could have created violent turbulence, generating the very first feeble magnetic seeds. A mechanism known as the Biermann battery effect is a prime candidate. Imagine a cloud of hot, swirling plasma where the pressure and density are not perfectly aligned. This misalignment can spontaneously generate electric currents, and from them, a weak magnetic field. It is a cosmic bootstrap creating something from almost nothing, but these initial fields would have been incredibly weak and disorganized. To build the powerful, structured fields we observe today, the universe needed an engine. That engine is the astrophysical dynamo, driven by the chaotic motion of turbulent gas and the powerful shear forces found in rotating galaxies and galaxy clusters. A dynamo can take a weak seed field and amplify it exponentially. The motions of the conducting plasma stretch, twist, and fold the magnetic field lines, transferring the energy of the movement into magnetic energy. Theorist Ethan Vishniak explored a crucial component called the alpha effect, a process driven by the helical turbulence in rotating fluids that is essential for sustaining and organizing these cosmic magnetic fields. We measure the strength and structure of these fields through a phenomenon called Faraday rotation. As light from a distant quasar or radio galaxy travels through a magnetized plasma, its polarization angle is subtly rotated. By analyzing this rotation across many different lines of sight, we can map the invisible magnetic landscape of the entire cosmic web. The fields in the Virgo cluster, for instance, are not random. They show a remarkable degree of coherence, aligned over distances that are difficult to explain. This presents a major theoretical challenge. How did such large-scale order emerge from what was likely a chaotic beginning? Some researchers speculate that dark matter may play a hidden role. If dark matter particles can interact with themselves, even weakly, their gravitational collapse could have generated turbulence that seeded magnetic fields even before the first stars formed. This would mean the cosmic magnetic web and the dark matter web grew up together, intertwined from the start. A lingering question connects this entire puzzle back to the universe's first light. Could these primordial magnetic fields have left their own faint signature on the cosmic microwave background? The search is on for a specific, twisted pattern in the CMB's polarization, a clue that would take us directly back to those first, frantic moments when the cosmos forged the tools for its own future construction. Our existence hinges on a fundamental cosmic imbalance. The universe should have created equal amounts of matter and antimatter in the Big Bang, a perfect symmetry that would have led to total mutual annihilation, leaving behind a sea of light and nothing else. Yet here we are in a world made of matter. Something must have tipped the scales. The search for that something leads us back to the universe's first picoseconds, to a pivotal event known as the electroweak phase transition. This was the moment when the electromagnetic force and the weak nuclear force, previously unified as a single force, split apart, fundamentally changing the nature of reality. Within that seething chaos, the conditions may have been just right to generate the slight excess of matter we see today, a process called baryogenesis. The foundational principles for how this could happen were laid out by physicist Andrei Sakharov. He identified three essential conditions that any theory must satisfy. First, there must be a process that violates Baryon number conservation. Baryons are particles like protons and neutrons, the building blocks of matter. The total number of baryons in the universe was thought to be a constant, but for an asymmetry to arise, this rule must be broken. In the early universe, hypothetical processes called sphalerons could have provided this violation. Think of a sphalerun as a quantum mountain pass. In the high-energy landscape of the early cosmos, these processes allowed matter to be transformed into antimatter and back again, effectively changing the baryon number and providing the raw mechanism for an imbalance. Sakharov's second condition is a violation of both charge conjugation symmetry, C, and charge parity symmetry, CP. C-symmetry means the laws of physics should be the same if you swap every particle with its antiparticle. CP symmetry means they should be the same if you do that swap and also mirror the coordinates. If these symmetries were perfectly upheld, the production of matter and antimatter would always be in perfect lockstep. But we know they are not absolute. We have observed CP violation in the laboratory. A prime example comes from the LHCb experiment at CERN, which studies particles called B mesons. The experiment has precisely measured how these mesons and their antimatter counterparts decay at slightly different rates. This tiny, measured difference is a smoking gun, proving that the laws of physics do, in fact, treat matter and antimatter slightly differently. But the CP violation we have found in the standard model of particle physics is far too weak to account for the vast cosmic imbalance we see. The third condition is a departure from thermal equilibrium. The early universe was a hot, dense soup where everything was in balance. In such a state, any process creating a little more matter would be immediately counteracted by its reverse. To break the symmetry permanently, the universe needed a sudden, dramatic shift that froze the imbalance in place. The electroweak phase transition could have been that very event. If it was a strongly first-order phase transition, it would not have been smooth and gradual. it would have been like the boiling of water, with bubbles of the new, separated force phase nucleating and expanding throughout the cosmos. At the walls of these expanding bubbles, conditions would have been wildly out of equilibrium, creating the perfect environment for Sakharov's three conditions to combine and generate a net Baryon number. Theorists like Mikhail Shaposhnikov have explored how this electroweak baryogenesis could work, often requiring new particles and forces just beyond our current knowledge. Other theories look to even higher energies. Leptogenesis proposes that the matter-antimatter asymmetry originated in the neutrino sector. Heavy, right-handed neutrinos could have decayed in the early universe, violating CP and producing a slight excess of leptons, particles like the electron. The Sphaleron processes then could have converted this lepton asymmetry into the Baryon asymmetry we live with today. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong forces, also naturally provide the conditions for baryogenesis at almost unimaginably high energies. The ongoing hunt for these answers is pushing our largest experiments to their limits. Particle colliders are trying to recreate the conditions of the electroweak phase transition, searching for any sign of new physics that could make a strong phase transition possible. Every measurement of CP violation, every search for a proton decay predicted by grand unified theories, is a test of these cosmic origin stories. The fact that we exist at all is direct evidence that the early universe was not perfectly symmetric. Baryogenesis is not a minor curiosity. It is a fundamental clue written into every atom in our bodies. It tells us with certainty that the standard model is incomplete and that the ultimate unification of nature's forces must contain within it the recipe for creating a universe that can one day look back and wonder why it is here at all. The universe was born in perfect symmetry, a state where all forces were one. During the very first moments of existence, the strong nuclear force that binds atomic nuclei, the weak force that governs radioactive decay, and the electromagnetic force that shapes light and chemistry were indistinguishable, merged into a single, unified power. This grand unification is the ultimate goal of theories that bear its name, grand unified theories or GUTs. They attempt to describe this primordial symmetry and its dramatic breaking as the cosmos expanded and cooled. The pioneering work of physicists like Howard Georgi, who proposed the first such model known as SU5, revealed a stunning possibility. In this framework, quarks, the particles that make up protons and neutrons, and leptons, like the electron, are not separate families but different facets of the same fundamental entity. They can, in theory, transform into one another. This radical idea has one profound and testable consequence: the instability of matter itself. It predicts that the proton, the seemingly eternal heart of every atom, should not last forever. It must eventually decay. This process of proton decay is incredibly slow, with a predicted lifetime far longer than the current age of the universe. To detect it, scientists have built massive, silent observatories deep underground, shielded from cosmic rays. Experiments like Super Kamiok and in Japan use vast tanks of ultra-pure water, waiting to catch the faint flash of light that would signal a single proton transforming into lighter particles. After decades of watching, no definitive decay has been seen. These null results have ruled out the simplest GUT models, including Georgi's original SU5, forcing theorists toward more complex and elegant ideas. This experimental patience is a direct test of the universe's first moments. The mechanism that broke the perfect symmetry of the grand unified force is thought to involve a cosmic version of the Higgs field. As the universe cooled, this field shifted into a new state, like water freezing into ice, and in doing so, it carved the distinct forces we know today. This phase transition did not happen smoothly everywhere. Think of a pot of boiling water. Bubbles of the new, broken symmetry phase would have formed and expanded. Where these bubbles met, the cosmic structure could have become tangled, creating topological defects. One of the most famous of these relics is the magnetic monopole. Unlike every magnet we have ever seen, which always has both a north and a south pole, a monopole would be a solitary north or south pole, a fundamental magnetic charge. These massive, stable particles should have been produced in vast numbers in the early universe. Their sheer abundance, according to calculations, would have overwhelmed the cosmos, making it far denser than what we observe. Where did they all go? The most compelling solution is cosmic inflation. The same period of monstrously fast expansion that smoothed the universe could have diluted the monopole density to virtually zero, sweeping these cosmic relics so far beyond our horizon that they became effectively non-existent. This elegant resolution of the monopole problem is one of inflation's great triumphs. Yet the search for even a single monopole continues, as its discovery would be irrefutable proof of those grand unified energies. This entire theoretical edifice also tackles the hierarchy problem, the puzzling question of why the weak force is so immensely stronger than gravity. Grand unified theories naturally incorporate scales that bridge this gap, suggesting a deep connection between the forces that our current physics sees as separate. The ongoing quest to understand grand unification forces us to confront the very stability of the world around us. The chair you sit on, the air you breathe, is made of protons that are, according to these theories, slowly ticking clocks. Their immense lifetime is a direct measure of the energy at which the universe once lived in perfect symmetry. This grand puzzle of unified forces and decaying matter leads us to another set of ghostly particles that flooded the young cosmos, particles that carry secrets about the largest structures in the universe, the cosmic neutrinos. Trillions of nearly massless particles are streaming through you at this very moment, a ghostly echo from the universe's first second of existence. These are cosmic neutrinos, and they form a background radiation far more ancient than the cosmic microwave background. When the cosmos was just 1 second old, it had cooled enough for these neutrinos to stop interacting with other matter and begin their endless journey across space. This cosmic neutrino background is a perfect fossil, preserving a snapshot of the infant universe in a way no other relic can. Yet detecting these ghosts is a monumental challenge, as they interact with matter so feebly that they can pass through light years of lead without a trace. Projects like Ptolemy aim to catch them not by waiting for a chance collision, but by looking for the faint imprint they would leave when interacting with a vast amount of radioactive tritium. Meanwhile, the Ice Cube Observatory at the South Pole uses a cubic kilometer of Antarctic ice as a detector, watching for the extremely rare flashes of light created when a high-energy neutrino from a distant cosmic event interacts with an atom in the ice. These are not the primordial neutrinos themselves, but their modern cousins, helping us understand the behavior of these elusive particles. The influence of cosmic neutrinos, however, is written across the cosmos in a way we can measure. For millions of years after decoupling, these particles streamed freely across the universe, their immense speed and weak interactions preventing them from collapsing into the gravitational wells that were forming the first galaxies. This free streaming effect smoothed out the distribution of matter on the smallest scales, effectively erasing some of the tiniest clumps of dark matter. We see the consequence of this today in the number of small dwarf galaxies orbiting our Milky Way. There are fewer than our models predict, and neutrinos are a prime suspect. Their light-footed dance also left a distinct mark on the cosmic microwave background. The specific pattern of hot and cold spots in the CMB's power spectrum, the blueprint of the early universe, is subtly altered by the presence and properties of these neutrinos. By analyzing this pattern with exquisite precision, cosmologists can effectively weigh the neutrino. We now know neutrinos have mass, but a puzzlingly tiny one, and this leads directly to the neutrino hierarchy problem. We have detected 3 types or flavors of neutrinos, but we do not know the order of their masses. Is the heaviest one significantly heavier than the other 2, or are they all nearly the same? The answer is crucial, as it points toward new physics beyond the standard model, and could even clarify the role of neutrinos in the universe's matter-antimatter asymmetry. Determining this mass hierarchy is a primary goal of next-generation experiments. The existence of even this minuscule mass has a gravitational effect that slows the overall growth of the cosmic web. Heavier neutrinos would have suppressed the formation of large-scale structure even more, so by mapping the vast filaments and voids of the universe, we are effectively placing an upper limit on how heavy these phantoms can be. This deep connection even extends to dark matter. If dark matter particles are also very light, like the theorized terral neutrino, they would exhibit similar wave-like behavior, further sculpting the distribution of galaxies in ways we are just beginning to model. The silent flux of cosmic neutrinos is a direct line back to a time before the first atoms formed. They are the universe's quietest witnesses, and by learning to read their subtle story, we gain a profound new window into the forces that shaped everything, including the nature of the universe's most missing components. Even the ordinary matter we are made of is playing a cosmic game of hide and seek. For decades, a simple but profound census has come up short. When we tally all the normal atoms in stars, galaxies, and the cold gas we can easily see, we find only about half of what should exist. The universe's predicted budget of ordinary matter, established by the flawless calculations of Big Bang nucleosynthesis, is missing a colossal amount. This is the missing Baryon problem, and the leading suspect is a vast, diffuse web of incredibly hot gas known as the warm-hot intergalactic medium, or WIM. Cosmologist Michael Scholl has emphasized that completing this Baryon census is critical, as these missing atoms are the essential raw material for cosmic structure. They are the hidden reservoir from which galaxies form and grow. Finding them means finding the other half of our visible universe. The challenge is that this WIM is so tenuous and hot that it emits almost no light of its own. It exists in a state that makes it practically invisible to conventional telescopes. To uncover it, astronomers have become cosmic detectives, using indirect and brilliant techniques. One method studies the light from incredibly bright, distant quasars. As this light travels for billions of years through the cosmic web, it passes through filaments of the WIM. Specific elements within that hot gas, like oxygen and neon, absorb very particular wavelengths of the quasar's light. The resulting quasar spectrum is not a clean rainbow, but a forest of absorption lines, each a tiny bite taken out of the light by a different cloud of intergalactic gas. By decoding this forest of lines, we can map the distribution and properties of the hidden WIM. Another powerful tool relies on the cosmic microwave background. When the ancient light from the Big Bang passes through a galaxy cluster, it interacts with the hot electrons in the cluster's gas. These electrons give the photons a slight energy boost through the Sunyaev-Zeldovich effect. By measuring this subtle distortion in the background radiation, we can weigh the hot gas in clusters, another piece of the missing matter puzzle. A crucial force in all of this is feedback from active galactic nuclei. When a supermassive black hole at the center of a galaxy feeds on matter, it can unleash tremendous blasts of energy. These outbursts pump heat and enriched gas out of the galaxy and into the vast intergalactic voids, helping to keep the WIM hot and diffuse. This process effectively hides the baryons by preventing them from cooling and collapsing to form new stars. Instruments like the Cosmic Origins spectrograph on the Hubble Space Telescope are at the forefront of this search. By staring at distant quasars for hundreds of hours, the COS can detect the faintest absorption signatures from these elusive intergalactic filaments. Each successful detection is like finding a single, specific needle in a cosmic haystack, slowly filling in the map of our hidden universe. Solving this mystery does more than just balance a cosmic ledger. It completes our picture of how the cosmic web functions, showing how matter cycles between galaxies and the intergalactic medium. This grand cycle of baryons, driven by the explosive feedback from black holes, is what ultimately regulates the birth and death of galaxies themselves. A supermassive black hole is not a cosmic vacuum cleaner lurking silently in a galaxy's core. It is a dynamic engine, a regulator whose furious activity dictates the life and death of its entire host galaxy. This intricate dance, known as co-evolution, reveals that the growth of a galaxy and the growth of its central black hole are inextricably linked. Astronomers like Sandra Faber uncovered a remarkable correlation, the M-sigma relation, which shows a direct proportionality between the mass of the central black hole and the velocity dispersion of stars in the galaxy's bulge. A more massive black hole means a larger, more tightly bound central cluster of stars. This is not a coincidence. It is the signature of a profound feedback loop. The engine of this feedback is the active galactic nucleus, or AN, a phase when the black hole is actively feeding. As matter spirals inward through an accretion disk, it is heated to millions of degrees, glowing brilliantly across the electromagnetic spectrum. But the true power emerges when magnetic fields twist this infalling plasma, launching jets of particles at nearly the speed of light. These relativistic jets, like the one famously erupting from the galaxy M87, can punch clear across intergalactic space for thousands of light years. Their impact is immense. They inject colossal energy into the surrounding galactic gas, the very reservoir for new stars. This creates a cycle of heating and cooling that can either trigger a starburst or quench star formation entirely. In one mode, the Axions outpouring can compress cold gas clouds, catalyzing the birth of new stars. In the other, more dominant mode, it acts as a cosmic blowtorch. The jets and radiation heat the galactic halo, preventing the gas from cooling and collapsing to form stars. This process, called quenching, is why many massive galaxies are no longer stellar nurseries but aging populations of old stars. The black hole effectively regulates its own food supply and the galaxy's growth. The origin of these supermassive giants remains a subject of intense study. Did they form from the direct collapse of immense gas clouds in the early universe, or did they grow from smaller stellar mass black hole seeds, gorging on gas over billions of years? The answer likely involves both paths. The case of M87 makes this abstract process tangible. We can see its magnificent jet, a testament to the raw power of its several billion solar mass black hole. That jet is not just a spectacular light show. It is pumping energy into the Virgo cluster, influencing the gas that surrounds not only M87 but its neighboring galaxies as well. This is how a black hole's influence extends beyond its own galactic borders. How do these titans, acting within their individual galaxies, collectively influence the grand architecture of the cosmic web? Their outflows help to keep the vast intergalactic voids hot and empty, and their energy regulates how galaxies cluster along the dark matter filaments. The silent, invisible hand of black hole feedback is one of the primary sculptors of the universe's largest structures. The silent flux of neutrinos and the hidden reservoirs of ordinary matter all point toward an inevitable cosmic destiny. Our universe is not a static stage, it is a story with a final chapter, and its ending is written in the nature of dark energy and the relentless march of entropy. Physicist Brian Greene often reflects on the profound implications of the second law of thermodynamics, which dictates that the universe's disorder must always increase. This leads to the most probable and perhaps most desolate finale, the heat death or big freeze. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate. All the usable energy in the universe gradually dissipates, stars burn out, black holes slowly evaporate via Hawking radiation, and over trillions upon trillions of years, the cosmos settles into a state of absolute equilibrium, a uniform, frigid sea of particles where no more work can be done, and no more stories can be told. Time itself, in any meaningful sense, would cease to exist. Yet this is not the only possible end. If dark energy is not a constant but a phantom energy that grows stronger over time, the outcome is far more violent. The expansion would accelerate without limit, eventually overcoming the very forces that hold reality together. First, galaxy clusters would be torn apart. Then, individual galaxies, stars would be ripped from their orbits, planetary systems would disintegrate. In the final moments, atoms themselves would be shredded, and finally, space-time would be torn asunder in a cataclysmic big rip. This dramatic end could, in some models, occur in as little as 22 billion years from now. A third possibility, the Big Crunch, offers a more cyclical vision. If dark energy were to decay or reverse, gravity could eventually regain dominance. The expansion of the universe would slow, halt, and then reverse. Galaxies would begin rushing toward each other, the cosmos heating up as it collapses back toward an ultra-dense state. This singularity could, in theories like the Big Bounce, be not an end but a rebound, a gateway to a new cosmic cycle. Roger Penrose's conformal cyclic cosmology presents a different kind of cycle, where the infinite expansion and evaporation of one universe becomes the low-energy, uniform starting point for the next. In his view, the end of time in one eon is conformally identical to the beginning of time in another, allowing for an eternal sequence of universes. These scenarios hinge on the precise value of the cosmological constant and the true nature of the quantum vacuum. The terrifying possibility of vacuum decay adds another layer. If our universe exists in a metastable vacuum, a bubble of true, stable vacuum could spontaneously form and expand at the speed of light, rewriting the laws of physics and erasing our reality in an instant. A thought experiment asks if a civilization could survive in such a dying universe. Could intelligent beings harness the last evaporating black holes for energy, or encode their consciousness into stable, fundamental particles, existing for near eternity in a state of near nothingness? This stark future forces a profound philosophical question. If the universe is destined for eternal silence or cyclical rebirth, what meaning can we assign to the grand narrative of cosmic evolution, to the rise of galaxies, planets, and life? Perhaps the meaning is not in the final state, but in the fleeting, beautiful complexity that emerges along the way. This search for purpose in the face of cosmic endings naturally turns our gaze outward, to the silent sky, and to the question of whether anyone else is out there to witness this story with us. This profound silence from the cosmos speaks volumes. If the universe is so vast and ancient, with billions of planets that could harbor life, why do we hear nothing but static? This is the heart of the Fermi Paradox, a question physicist Enrico Fermi famously posed over lunch one day, asking simply, "Where is everybody?" The universe should be teeming with civilizations, yet we observe no signals, no visits, no engineering on stellar scales. The Drake equation provides a framework for this puzzle, multiplying factors like the rate of star formation, the fraction of stars with planets, and the number of worlds in the habitable zone. It then ventures into the profound unknowns, the fraction where life actually appears, where intelligence evolves, and most critically, where civilizations develop the technology and the will to communicate across the void. The final term in the equation is the most haunting, the length of time such civilizations release detectable signals into space. This is where the great filter hypothesis emerges. Think of it as a cosmic gauntlet, a developmental stage so difficult that almost no life forms survive it. This filter could lie in our past, making the emergence of intelligent life itself astronomically rare. Or, terrifyingly, it could lie in our future, a common catastrophe that awaits all technological species, from self-destruction through war or ecological collapse to an external threat like a gamma ray burst sterilizing entire galactic regions. These bursts are cosmic lightning strikes, and one occurring too close could reset the evolutionary clock on a planet, effectively filtering out life before it becomes interstellar. The silence we hear might be the echo of countless civilizations that blinked out of existence. Economist Robin Hanson articulated this chilling possibility, suggesting that something must be preventing the cosmos from being visibly filled with life. We might be living in an anthropic shadow, a time and place where we can only exist because the great filter is behind us, and we are among the first to emerge, or tragically, because we have yet to face the true test that eliminates everyone else. Consider the potential fates of civilizations using the Kardashev scale. A Type 1 civilization harnesses all the energy of its home planet. A Type 2, like a hypothetical culture building a Dyson sphere, captures the entire output of its star. A Type 3 commands the energy of a galaxy. If such entities existed, their technosignatures would be immense, reshaping star systems or lighting up the infrared spectrum with waste heat. We see no evidence of this. This absence suggests another possibility, the zoo hypothesis. Perhaps advanced civilizations are out there, but they are deliberately avoiding contact, observing us as we would a nature preserve, or simply finding us too primitive to be of interest. The sheer cosmic timeline adds another layer. The universe is 13.8 billion years old, and our technological civilization is less than a century old. Other intelligences could have risen and fallen billions of years ago. Their signals faded into background noise, or they may have evolved into forms of post-biological existence we cannot even perceive. The silence is not necessarily empty. It might be a library, a graveyard, or a wilderness. Does this paradox point to a bleak future where intelligent life is a fleeting, self-extinguishing flame, or does it offer a hopeful, if lonely, mandate? We are the universe becoming aware of itself, and the responsibility to answer this question, to ensure our voice is not added to the silence, may now rest entirely with us. This search for meaning in the quiet connects directly to the nature of reality itself, to the idea that information is the most fundamental currency of existence. The profound silence of the cosmos might be a clue that reality is not what it seems. What if the universe is not a collection of fields and particles, but a vast, ongoing computation? This radical idea, known as digital physics, suggests that space-time, matter, and energy are not fundamental. They emerge from something more basic, the processing of information. The universe, in essence, may be a quantum computer, The roots of this thought stretch back to physicist John Archibald Wheeler and his famous phrase, "it from bit." He proposed that every particle, every force, every event in the cosmos derives its existence from binary answers to yes or no questions. The physical world is not just described by information, it is made of information. The most compelling evidence for this comes from the most extreme objects in the universe, black holes. Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, which is a measure of its information content, is not proportional to its volume, but to the surface area of its event horizon. This was a revolutionary insight. It suggested that all the information needed to describe everything within a three-dimensional region of space could be encoded on its two-dimensional boundary. This is the heart of the holographic principle, a concept Leonard Susskind and Gerard T. Hooft developed. Our perceived three-dimensional reality could be a holographic projection from a distant, two-dimensional surface. In string theory, this idea takes a precise mathematical form through the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. It posits a perfect duality between a gravitational theory in a warped space and a quantum field theory without gravity living on its boundary. To make this concrete, imagine a vast cosmic sphere that encloses our entire observable universe. The frenetic, quantum interactions of fundamental particles on that outer surface are not a separate reality. They are the source code for the world we experience within, the stars, the planets, and you are a magnificent three-dimensional projection generated by that two-dimensional data. This immediately raises the simulation hypothesis. If the universe is a computation, could it be a simulation running on a hyper-advanced computer in some other reality? While this is a popular philosophical idea, most physicists see it as untestable and missing the point. The deeper question is not whether our universe is a simulation in some other universe, but whether the fundamental nature of reality is inherently computational right here. This leads to the ultimate limits of computation. Is there a maximum amount of information a region of space can contain? Is there a smallest possible unit of spacetime, a pixel of reality? The Planck length, a scale so tiny that our current laws of physics break down, might represent this fundamental resolution of the cosmos. How could we ever test such an ethereal concept? Scientists are looking for a potential pixelation of spacetime in the light from distant gamma-ray bursts. If spacetime is truly digital, then very high-energy photons traveling across the universe might be slightly slowed down depending on their wavelength, a subtle effect that future observatories might one day detect. Another test involves the cosmic microwave background. If the universe is a hologram, the patterns in this ancient light might show statistical anomalies, a specific kind of noise that would betray its digital origins. So if the universe is a computation, what is it calculating? It seems to be calculating itself, its own evolution. The endless, complex interactions of quantum bits generate the flow of time, the force of gravity, and the emergence of structure. This computational view reframes the greatest puzzle of all, the question of cosmic initial conditions. The Big Bang was not just a moment of immense density and temperature. It may have been the moment the cosmic computer booted up when the first bit was flipped and the program of reality began to run. The universe could have been anything at all. An endless void, a chaotic storm of radiation, or a fleeting puff of particles that instantly collapsed. Yet, against all apparent odds, it began with a very specific, highly ordered state, a set of initial conditions that would eventually allow for galaxies, planets, and conscious life to emerge. This is the problem of initial conditions, and it asks the most fundamental question of all: why these laws and why this universe? The cosmic starting point was not random. It possessed a low entropy, a state of exquisite order that set the direction for the arrow of time itself. To understand how profound this is, picture the set of all possible universes, a vast library containing every conceivable combination of physical laws and constants. In nearly every volume in this library, the story ends almost immediately. Universes where gravity is too strong collapse back on themselves in a flash. Others where the nuclear forces are too weak never form atoms. Our universe appears to be a singularly lucky draw from this cosmic stack. Stephen Hawking, working with James Hartle, grappled with this by proposing that the universe has no boundary in time. Their no-boundary proposal suggests we replace the idea of a singular beginning with a smooth, curved geometry, like the surface of a sphere. In this view, the question of what happened before the Big Bang becomes meaningless, much like asking what is north of the North Pole. The beginning was not a point in time, but a point where time, as we know it, emerged. This idea is described mathematically by the wave function of the universe, a solution to the formidable Wheeler-DeWitt equation. This equation attempts to describe the entire cosmos in a single, timeless quantum state. It paints a picture where the universe does not evolve in time, but rather, all possible configurations simply exist. Our experience of a flowing present is what emerges from this deeper, static reality. This leads directly to the multiverse hypothesis. Physicist David Deutsch argues that if our best theories predict multiple universes, we should take that prediction seriously. In the eternal inflation scenario, our bubble universe is just one of countless others, each with its own random set of physical laws. In the string theory landscape, there are perhaps 10 to the 500 possible vacuum states, each a different universe with different particles and forces. We find ourselves in one that permits our existence because we could not exist anywhere else. This is the anthropic selection effect. It is not that the universe was designed for us, but that we are a product of a universe that accidentally has the right conditions. To see how delicate this balance is, consider a thought experiment. Imagine a universe where the weak nuclear force which governs radioactive decay simply did not exist. In our universe, this force is crucial for the supernova that scatter heavy elements like carbon and oxygen across space. Without it, there would be no planets, no chemistry, and no life. The fine-tuning is staggering, yet the multiverse answer introduces its own deep puzzle, the measure problem. In an infinite multiverse, every possible event occurs an infinite number of times. How do we assign probabilities to anything? What does it mean to say our universe is unlikely if there are infinite copies of it? This pushes the question into the realm of philosophy. Does a universe require a first cause, or can it simply be a brute fact of existence? The search for a final theory, a theory of everything, is ultimately a search for an explanation so compelling that it uniquely predicts the initial conditions we observe. We are left wondering if the cosmos is the result of a timeless mathematical principle, or if we are simply living in one lucky ticket in an infinite cosmic lottery where the winning numbers allowed for a story to be told. Our cosmic story is ultimately a search for purpose. Does the grand narrative of the universe, from the Big Bang to the emergence of life, point toward an underlying goal, or are we simply the product of a blind and mechanical process? This question sits at the intersection of cosmology and philosophy, forcing us to confront the ultimate why. The teleological argument, the idea that the universe appears designed for a purpose, finds new expression in the staggering fine-tuning of physical constants. Yet the multiverse offers a starkly different interpretation. If an infinite number of universes exist, then a handful must, by pure chance, have the right conditions for life. Our existence here is not evidence of design, but of a cosmic selection effect. As physicist Bernard Carr, a key proponent of the Anthropic Principle, has argued, what we can observe must be restricted by the conditions necessary for our presence as observers. This does not answer why the multiverse itself exists with laws capable of generating such variety. The problem of why there is something rather than nothing remains the most profound mystery of all. Every cosmological model, from ancient myths of world eggs and primordial seas to our modern scientific frameworks, is an attempt to answer this fundamental question. These stories reflect our deep-seated need to find a place within the cosmos, to see our lives as part of a meaningful whole. In a potentially infinite multiverse, the concept of ethical responsibility takes on a strange new dimension. If every possible choice is played out in some other reality, does that diminish the significance of our decisions here and now? Does it absolve us of consequence, or does it place an even greater weight on the unique, conscious narrative we are crafting in this particular cosmic branch? Philosopher Tim Maudlin challenges us to think deeply about the nature of time itself, arguing that its passage is a fundamental and irreducible feature of reality, not an illusion. If he is correct, then cosmic evolution is a genuine unfolding, a true story with a past that is fixed and a future that is open. This stands in stark contrast to the block universe view, where the entirety of history is eternally present. The simulation argument pushes these philosophical boundaries even further. If consciousness is the one undeniable fact of our existence, could the entire cosmos be an elaborate construct designed to foster it? Or is consciousness itself the fundamental reality, with the physical universe being its manifestation? The history of science shows a steady demotion of humanity's central place, from the Earth being the center of the cosmos to us being inhabitants of a tiny planet around an average star. Yet, the return of the observer through quantum mechanics and the Anthropic Principle suggests our role might be more significant than we thought. We are the universe becoming aware of itself. How then do we test these profound philosophical ideas? The tools are found at the frontiers of physics. The search for a complete theory of quantum gravity, the precise measurement of the cosmic microwave background's anomalies, and experiments probing the nature of dark matter and dark energy are not just technical pursuits. They are empirical probes into the very nature of reality, seeking clues that could tip the scales between a universe with a deep, underlying logic and a cosmos of sheer, random accident. The meaning we find is not written in the stars but forged in our quest to understand them. This relentless drive to comprehend our origins, from the first quantum fluctuation to the vast cosmic web, is perhaps the most human thing about us. It connects our fleeting lives directly to the grandest narrative of all, and it compels us to look ahead, to the final, practical challenge of unifying our deepest theories into a single, coherent picture of existence. The silent questions hanging over cosmology demand answers written in light, gravity, and ghostly particles. Our grand theories of cosmic evolution are only as strong as the data that supports them, and a new generation of observatories is now collecting that evidence. Imagine an array of machines spanning the globe and reaching into space, each designed to catch a different whisper from the cosmos. The James Webb Space Telescope peers into the infrared, its gold-plated eyes seeing the first galaxies being born. Project scientist Nora Luchtgendorf explains that JWST is not just taking pretty pictures. It is a time machine, measuring the precise chemistry of those infant stars to understand how they assembled so quickly after the Big Bang. Meanwhile, the Laser Interferometer Gravitational Wave Observatory, LIGO, feels the subtle shudders in spacetime itself, ripples from colliding black holes that tell a story gravity alone can share. This is multi-messenger astronomy, the powerful practice of listening to the universe with more than one sense. By combining what we see with light and what we feel with gravity, we get a complete picture of the most violent events, like a neutron star collision that was heard as a gravitational wave chirp and seen as a brilliant kilonova flash. Each type of observation reveals a different layer of truth. The cosmic microwave background, mapped in exquisite detail by the Planck satellite, gives us a baby picture of the universe. The Lyman alpha forest, a bizarre pattern of absorption lines in the light of distant quasars, acts as a cosmic thermometer and map, charting the vast, invisible filaments of the warm-hot intergalactic medium where the missing baryons hide. Massive galaxy surveys like those conducted by the Vera C. Rubin Observatory will catalog billions of galaxies, tracing the dark matter backbone of the cosmic web in 3 dimensions and across billions of years. But these delicate measurements are fraught with challenges. The biggest enemy is often systematics, not the faintness of the signal but subtle errors in the instruments themselves or in our models of the atmosphere that can mimic a cosmic discovery. This is why the Hubble tension is such a focal point. The conflict between the measured expansion rate of the universe using the early cosmos and the rate measured with nearby stars is not just a number, it is a potential crack in our standard model. Is it a sign of unknown systematics, or is it evidence for new physics, like a strange form of dark energy that evolved over time? New data from JWST is already being used to recalibrate the cosmic distance ladder, checking and rechecking every rung to see if the tension remains. Underground, in abandoned mines and deep beneath mountains, another hunt is underway. Experiments like LUX Zeppelin and Xeno NNT sit in profound silence and cold, waiting for the once-in-a-lifetime shudder of a dark matter particle colliding with the nucleus of a xenon atom. In the clear ice of the South Pole, the ice cube detector watches for the rare flash of a neutrino interaction, trying to catch the ghostly background from the universe's first second. The next decade promises even greater revelations. The space-based gravitational wave observatory LISA will listen for the low-frequency hum of merging supermassive black holes, a sound that has been filling the cosmos since its earliest epochs. The Nancy Grace Roman Space Telescope will conduct wide-field surveys to probe the nature of dark energy with a precision we can barely imagine today. These are not just bigger telescopes, they are smarter tools designed to test specific predictions from our boldest theories. Will they confirm a universe shaped by eternal inflation or point toward a cyclic model? The data streams now flowing from these incredible machines are the raw material for the next great interpretation of reality, forcing theoretical innovation to either stand firm or gracefully fall away. Mathematics provides the silent architecture for our physical reality, a language so precise it often predicts the universe's behavior before we ever observe it. This deep connection suggests that cosmic evolution might be guided by mathematical principles we are only beginning to decipher. Beyond the familiar geometry of Einstein's relativity, new mathematical landscapes are emerging, offering radical new interpretations of the cosmos. Elaine Kahn's framework of non-commutative geometry, for instance, reimagines the fabric of spacetime itself. In this view, the very coordinates of space may not commute, meaning that measuring position in one direction could affect measurement in another, suggesting a fundamental granularity to reality at the tiniest scales. This isn't just abstract symbol shuffling. It implies that the smooth, continuous space we perceive is an illusion emerging from a deeper quantum structure, much like the smooth surface of a pond emerges from the chaotic dance of countless water molecules. This drive for mathematical consistency is a powerful engine for theoretical discovery. The entire edifice of particle physics, for example, is built upon the language of symmetry groups. The Standard Model classifies every known particle and force through specific mathematical symmetries. The hunt for the Higgs boson was not a random fishing expedition. It was a direct consequence of this mathematical framework. Theorists used group theory to deduce that a field permeating all of space was necessary to give particles their mass, and the Higgs boson was the predicted signature of that field. Its eventual discovery at the Large Hadron Collider was a stunning validation of mathematics as a prophetic guide to nature's secrets. This uncanny ability of math to describe the physical world so perfectly is what physicist Eugene Wigner called its unreasonable effectiveness. Why should human-invented abstractions like algebra or calculus have such power to unveil the laws of the cosmos? Is mathematics a human discovery of a pre-existing Platonic realm, or is it merely a useful invention, a tool that fits reality because we have evolved to recognize useful patterns? Lee Smolin offers a provocative alternative, arguing that the laws of physics are not eternal and transcendent, but rather evolve in time, selected by a form of cosmic natural selection within a multiverse. In this view, mathematics is not a static truth but a dynamic language describing a universe in flux. This debate strikes at the heart of what reality is. Another frontier is category theory, a highly abstract branch of mathematics sometimes called the mathematics of mathematics. It focuses on the relationships between objects rather than the objects themselves. Some physicists believe this relational approach is the key to quantum gravity, providing a framework where space and time are not fundamental ingredients but emergent properties arising from a network of deeper connections. The concept of emergence is central here. Complex phenomena like consciousness or life itself arise from the collective behavior of simpler parts, and the laws that govern them may not be reducible to the laws of their components. Similarly, the force of gravity and the flow of time may not be fundamental, but may emerge from the intricate interplay of countless quantum events, much like the wetness of water emerges from the collective behavior of H2O molecules, a property absent from any single molecule. But how do these elegant, abstract theories make the leap from the blackboard to the cosmos? The crucial bridge is built through computational simulation. Theorists translate their mathematical models into vast computer codes, creating digital universes that obey proposed new laws. They can watch as virtual galaxies form, cosmic structures evolve, and hypothetical particles interact. By comparing these digital universes against our precise observations of the real one, we can test which mathematical visions hold up. A theory might be mathematically beautiful, but if the universe it simulates in a supercomputer looks nothing like our own, it must be revised or abandoned. This iterative dialogue between pure mathematics, theoretical physics, and computational modeling is how our deepest abstractions are forged into testable science, pushing our understanding of cosmic evolution into realms our intuition alone could never reach. These digital universes are born from lines of code running on the world's most powerful supercomputers. This is computational cosmology, a field where we recreate the entire history of the cosmos inside a machine, not to replace observation but to understand it. We begin with a near-uniform sea of dark matter, seeded with the exact same tiny quantum fluctuations we see in the cosmic microwave background. Then we press play and let gravity work its magic over billions of simulated years. The dark matter clumps and collapses, weaving the cosmic web of filaments and voids, a ghostly skeleton upon which galaxies will later form. Pioneering efforts like the Millennium Simulation, led by cosmologist Carlos Frenk, were landmark achievements in this endeavor. Frenk has described these simulations as virtual laboratories, allowing us to perform experiments on the universe itself, testing how different physical laws would shape its large-scale structure. To build these virtual cosmos, scientists use sophisticated techniques. N-body simulations track the gravitational dance of billions of dark matter particles, each one representing a vast swarm of the real thing. But dark matter alone cannot make a galaxy. For that, we need hydrodynamics, which models the complex behavior of normal matter, the gas that cools, condenses, and eventually ignites into stars. The most critical and most difficult ingredient to simulate is feedback. We must program in the explosive energy from supernova and the fierce winds from supermassive black holes. These forces blow gas away, halting star formation and preventing galaxies from growing too large, a process crucial for creating the diverse galaxy population we observe. A project like Illustris TNG uses these combined methods to study phenomena like galaxy quenching, showing how a black hole's outburst can heat a galaxy's halo of gas, effectively shutting down its star-forming factories and leaving it a red and dead relic. Yet these digital universes are not perfect mirrors of our own. They face immense challenges, starting with resolution. Even the most powerful supercomputers cannot simulate every single star in a galaxy. Instead, they use particles that represent millions of solar masses, forcing them to approximate the small-scale physics that drives galactic evolution. The entire simulation also hinges on the initial conditions we feed it. If we start with the wrong recipe for those primordial fluctuations, the entire cosmic story that unfolds will be wrong. This is why code comparison projects are so vital. Different research groups around the world will run the same simulation with their own unique software, checking to see if they get the same result. If they do not, it reveals hidden assumptions or bugs in our digital cosmos. Perhaps the most profound limitation is cosmic variance. There is only one real universe to observe. Our observable cosmos, vast as it is, might just be one possible outcome of the laws of physics, a single random draw from a distribution of possibilities. A simulation can only tell us what a typical universe should look like based on our models. If our real, observed universe is atypical in some way, a statistical fluke on the grandest scale, then no simulation will ever perfectly match it. This humbling thought suggests that even with infinite computing power, we might only ever understand the probabilities of cosmic evolution, not its singular, definitive story. Our entire view of the cosmos is built from a single data point. We have only one universe to observe, and we are stuck inside it, limited to the light that has reached us over 13.8 billion years. This fundamental constraint introduces a deep uncertainty into cosmology known as cosmic variance. It is the statistical noise that arises because we cannot average our measurements over multiple universes. We are trying to understand the entire cosmic population from a single specimen. This is not a small technicality. It places a hard ceiling on how well we can ever know the true, global properties of reality. Even our most precise maps, like the cosmic microwave background, are subject to this intrinsic sampling error. The pattern of hot and cold spots we see is just one possible realization of the underlying physics. Another universe born from the same laws might have a slightly different arrangement of those spots, and its astronomers would measure slightly different values for its large-scale properties. Statisticians working with cosmologists use sophisticated tools like Bayesian inference to quantify these uncertainties. They ask, given the one universe we see, what is the probability that a particular theory about its origins is correct? This framework allows them to fold cosmic variance directly into the error bars of every major cosmological parameter. A powerful illustration of how our perspective shapes reality is the dipole anisotropy in the cosmic microwave background. The most prominent feature in this ancient light is not a primordial feature at all, but a Doppler effect caused by our own motion. Our solar system is rushing through space, and this motion makes the CMB appear hotter in the direction we are heading and colder behind us. We must carefully subtract this local signature to see the true, underlying fluctuations imprinted at the Big Bang. This is a constant reminder that we are not privileged observers at a cosmic rest frame. Our view is always and inevitably from a moving platform. The challenge of cosmic variance becomes even more acute when we study the largest structures. When we count galaxy clusters or map the vast cosmic voids, we are taking a sample of a single, finite universe. The distribution we see could, by pure chance, be slightly over-dense or under-dense in our particular neighborhood. This sample variance is a direct manifestation of cosmic variance on the scale of the cosmic web. Future surveys like the Legacy Survey of Space and Time, LSST, will map billions of galaxies, but they will still only be cataloging our one observable patch. They will reduce the uncertainty, but they can never eliminate it entirely. This limitation strikes at the heart of theories like the multiverse. If an infinite froth of bubble universes exists, each with different physical constants, how could we ever confirm it? We are forever confined to our own bubble, unable to peek into the next. Any measurement we make here only tells us about the local bylaws of our cosmic domain. The search for anomalies in the CMB, like the mysterious cold spot or the unexpected alignments of the largest ripples, takes on a new significance in this light. Are these genuine clues to new physics, or are they simply statistical flukes, the cosmic equivalent of rolling the same number on a die multiple times in a row? Without other universes to compare against, we may never know for sure. This profound uncertainty forces a humbling conclusion. We may never be able to prove that our universe is typical. The cosmos we see might be a rare outlier, a special quiet corner in a more chaotic multiverse, or it might be the only one. Our entire scientific story is written from a single, unverifiable point of view. A stubborn crack has appeared in our most trusted cosmic map. The universe is expanding, but we cannot agree on how fast. This is the Hubble Tension, a discrepancy that emerges from two different ways of measuring the cosmos. One method uses the cosmic microwave background, the ancient light from the infant universe, to calculate an expansion rate. The other relies on a cosmic distance ladder built from pulsating stars and exploding supernova in our modern cosmic neighborhood. These two paths, one looking back to the beginning and one examining the present day, yield answers that stubbornly refuse to match. Astronomer Wendy Friedman, whose pioneering work helped to solidify this tension, has noted that the disagreement is now too significant to dismiss as simple error. It suggests that our standard model of cosmology, the lambda cold dark matter model, might be missing a crucial ingredient. One compelling proposal is early dark energy, a transient form of this mysterious force that could have briefly surged in the universe's first few 100,000 years, subtly altering the early expansion rate and leaving behind the conflicting measurements we see today. This would mean dark energy is not a constant but a dynamic actor that has changed its role throughout cosmic history. Another profound puzzle is written in the stars themselves. According to the pristine calculations of Big Bang nucleosynthesis, the first few minutes of the universe should have forged a specific amount of lithium. Yet when we look at the oldest stars in our galaxy, we find only about a third of the predicted lithium. This lithium problem is a direct contradiction between our theory of the universe's first nuclear furnace and the actual fossil evidence we observe. The missing lithium points to a gap in our understanding of nuclear physics under those extreme primordial conditions, or perhaps to the influence of exotic particles like decaying dark matter, which could have disrupted the delicate nuclear chain reactions in the cosmos's first moments. Even our sharpest image of the young universe, the Planck satellite's map of the cosmic microwave background, is not perfectly smooth. It contains strange, large-scale anomalies. A vast cold spot, much larger and cooler than expected, stretches across the sky. The largest ripples in this ancient light appear mysteriously aligned with the plane of our own solar system, a correlation so unlikely it has been dubbed the axis of evil. While their statistical significance is still debated, these features whisper that our universe might not be the same in all directions, challenging a foundational assumption of modern cosmology. Consider the curious case of the Planck mass. In the quest for a theory of quantum gravity, this is the natural unit of mass, a fundamental scale where gravity is expected to become as strong as the other forces. Yet when physicists try to use this mass to construct a viable dark matter particle, the numbers often do not work. This theoretical outlier, this mismatch between a beautiful mathematical idea and the requirements of the real world, forces a profound re-evaluation. It pushes theorists to explore entirely new classes of particles and interactions, demonstrating how a single anomaly can redirect an entire field of research. The history of science is filled with such moments where a data point that did not fit, a measurement that refused to conform, became the key that unlocked a deeper reality. These cosmological discrepancies are not mere noise. They are the universe trying to tell us something we have not yet learned to hear. What if our entire story of cosmic evolution is awaiting a single, crucial correction, hidden in plain sight within these frustrating and beautiful inconsistencies? The hiss in the horn antenna was relentless, an unexplained static that plagued every observation. Arno Penzias and Robert Wilson tried everything to eliminate it, even scrubbing away what they called a white dielectric material left by pigeons. Nothing worked. That persistent noise, that cosmic annoyance, was not a technical flaw. It was the echo of creation itself, the cosmic microwave background radiation. Their accidental discovery in 1965 provided the first direct evidence for the Big Bang, transforming cosmology from pure theory into observational science. Penzias himself later reflected that they were looking for nothing and they found something. This is the power of serendipity in science, where a frustrating problem becomes a window into the universe's deepest secrets. Decades later, two teams led by Saul Perlmutter were racing to measure the universe's deceleration. They were using distant supernovae as cosmic mileposts, expecting to see the expansion slowing under gravity's pull. Instead, the data revealed the opposite. The universe was not slowing down at all. It was speeding up, driven by a mysterious force we now call dark energy. Perlmutter described the moment as a true eureka experience, a shocking result that forced them to question everything. They had stumbled upon the greatest cosmic surprise of the late 20th century. These stories are not outliers, they are central to the story of cosmic discovery. Long before dark energy, Fritz Zwicky was studying the Coma cluster of galaxies in the 1930s. He noticed the galaxies were moving so fast that the cluster's visible mass could not possibly hold them together. He proposed the existence of Dunkel Materie, dark matter, to account for the missing gravity. His idea was largely ignored for decades, a solution in search of a problem until Vera Rubin's work confirmed it. Then there is the case of Jocelyn Bell Burnell. As a graduate student in 1967, she detected a strange, pulsing signal in her radio telescope data, a rhythm so precise she and her supervisor half-jokingly labeled it LGM-1 for little green men. It turned out to be the first pulsar, a rapidly spinning neutron star, a new class of object whose discovery opened a new window into stellar corpses and extreme physics. Sometimes the key is not in the data you seek, but in the data you initially dismiss. The Boom-Ran-G balloon experiment, which flew over Antarctica, was designed to take a detailed picture of the cosmic microwave background. Scientists expected to see a random pattern of hot and cold spots. What they found was a startlingly clear peak in the data, a specific size to the largest ripples. This single, serendipitous measurement provided the first strong evidence that the geometry of the universe is flat, a cornerstone of our modern cosmological model. It was a result hidden in the noise, waiting for an open mind to recognize its significance. How do we cultivate this kind of fortunate accident? It requires a scientific culture that values curiosity over confirmation, that allows researchers to pursue anomalies and ask questions that seem to lead nowhere. It demands diverse teams who can look at the same frustrating signal and see different possibilities. Most of all, it requires building instruments that collect a broad spectrum of information, creating rich archives where future discoveries can lurk, waiting for a fresh perspective to find them. The next revolution in cosmology might not come from a targeted experiment designed to test a specific theory. It might be hiding in the static of a new telescope, in a glitch in a supercomputer simulation, or in a data set that everyone else has overlooked. The universe is full of whispers, and sometimes the most important message is the one we never thought to listen for. Cosmic cartography is about to leap into a new dimension. The next generation of observatories, both on the ground and in space, will not simply take better pictures, they will fundamentally change the kinds of questions we can ask. The Nancy Grace Roman Space Telescope, for instance, is not just another Hubble. Its mission is to conduct a colossal survey of the sky, mapping the cosmos in 3 dimensions to trace the subtle influence of dark energy across billions of years. It will measure the shapes and positions of millions of galaxies, hunting for the telltale distortions caused by dark matter and tracking how the cosmic web has stretched over time. This is not about finding a single object, but about understanding the overall architecture of reality. As mission planner David Spergel has described, the goal is to measure the universe's expansion history with such precision that we can finally distinguish between a static cosmological constant and a dynamic dark energy field like quintessence. The data could reveal if dark energy has been changing, a discovery that would rewrite our forecast for the ultimate fate of everything. Simultaneously, a new kind of ear will be listening to the universe. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves at frequencies far lower than ground-based observatories can perceive. It will hear the mergers of supermassive black holes, events so colossal they send ripples through spacetime that take years to pass. LISA's true promise, however, lies in probing the universe's first moments. It might detect the primordial gravitational waves generated by cosmic inflation, a faint hum from the very birth of spacetime. This would be a direct observation of the quantum gravity era, a realm forever hidden from traditional telescopes. Think of it as hearing the universe's first cry, rather than seeing its baby picture. On Earth, projects like CMB Stage 4 are pushing the boundaries of what we can learn from that ancient light. By mapping the polarization of the cosmic microwave background with microscopic precision, these telescopes are searching for a specific swirling pattern, a signature called B modes. Finding this pattern would be the smoking gun for inflation, confirming that the universe underwent a period of exponential expansion. But the implications run even deeper. The precise properties of these B modes could reveal the energy scale at which inflation occurred. telling us if gravity was unified with the other forces and potentially offering clues about the existence of extra dimensions predicted by string theory. The data could even allow us to weigh the cosmic neutrino background with unprecedented accuracy, finally solving the neutrino mass hierarchy problem. The potential for a transformative discovery is immense. Imagine if one of these instruments detected evidence of cosmic strings. These are not strings in space, but defects in the fabric of spacetime itself, hypothetical one-dimensional cracks that would have formed during a phase transition in the early universe. A cosmic string would be a thread of pure energy thinner than a proton but stretching across the cosmos, with the mass of a mountain range packed into every inch. Its passage would create a unique double image of a distant galaxy and leave a sharp, step-like discontinuity in the cosmic microwave background. Finding one would be direct proof of grand unified theories, a relic from the universe's first trillionth of a second. This is the scale of discovery we are now approaching, where theories that seem like pure mathematics could suddenly become observable physics. These missions represent a global effort, a testament to humanity's shared curiosity. Their success, however, depends on more than just engineers and scientists. It relies on a public that understands and supports this profound quest to read the story of the universe. The data flowing from these new eyes and ears will not just provide answers, it will redefine the mysteries, inviting everyone to look up and wonder what comes next. That profound sense of connection to the cosmos is not a privilege reserved for scientists with giant telescopes. It is a story meant for everyone, a narrative that can reshape how we see our world and our place within it. We are living in a golden age of cosmic communication, where the wonders of the universe are translated into experiences that ignite curiosity in people of all ages and backgrounds. Think of the hushed awe inside a planetarium dome, where a starry sky is projected not just above, but all around, immersing the audience in a journey to the edge of a nebula or the dawn of time itself. This is more than a show, it is an emotional and intellectual portal, making the vast scales of the cosmos feel tangible and immediate. Science communicator Neil deGrasse Tyson often speaks to this power, arguing that the choice to become a scientist is not born from a textbook, but from a moment of inspiration, a spark of wonder that makes the universe feel accessible. That spark is what drives public engagement, turning abstract equations into a shared human adventure. One of the most powerful tools for this is citizen science, where anyone with an internet connection can contribute to real research. Projects like Galaxies Zoo invited the public to help classify millions of galaxies, a task that human intuition does better than any algorithm. Hundreds of thousands of people participated, not only accelerating science but also feeling a genuine sense of ownership in the cosmic map we are building together. This collaborative spirit extends to social media, where astronomers and institutions share breathtaking images from the James Webb Space Telescope, breaking down the latest discoveries in real time with stunning visuals and clear, concise language. The goal is not to dumb down the science but to clarify it, to find the human story within the data. This is where art and science merge in a vital partnership. A data visualization artist can take the raw numbers of a supercomputer simulation and transform them into a swirling, dynamic flight through the cosmic web, allowing us to see the invisible architecture of dark matter. These artistic interpretations are not just illustrations, they are tools for understanding, helping our minds grasp structures that are otherwise too large and too strange to comprehend. The impact of this shared cosmic perspective is perhaps best captured by a single, humble image, the pale blue dot. Taken by the Voyager 1 spacecraft from beyond Neptune, it shows our world as a tiny, pale speck of light suspended in a sunbeam. Carl Sagan's reflection on that image echoes through the decades, reminding us that every human being who ever lived, every joy and every sorrow, has happened on that mote of dust. This is the ultimate gift of cosmology, a planetary perspective that transcends borders and reminds us of our shared fragility and responsibility on this small world. How does sharing the story of cosmic evolution enrich humanity? It gives us a context for our existence, a grand narrative that is both humbling and empowering. It fosters critical thinking, inspires the next generation of explorers, and provides a unifying vision of reality built on evidence and wonder. When we understand that the atoms in our bodies were forged in the hearts of long-dead stars, we are not just learning a fact, we are remembering our lineage. We are the universe becoming aware of itself, and by sharing that story, we ensure that this awareness continues to grow. We stand at a unique crossroads in cosmic history, a fleeting moment where the universe can look back upon itself and ask why. The entire 13.8 billion-year saga, from the first hydrogen atoms to the swirling spiral of the Milky Way, has led to a species that can trace that very lineage. Carl Sagan captured this beautifully with his cosmic calendar, compressing the entire history of the universe into a single year. On this scale, the Big Bang occurs at the first second of January 1st. Our solar system does not form until early September. All of recorded human history occupies just the final few seconds of December 31st. In the vastness of cosmic time, we are an incredibly recent development, a whisper at the very end of the story. Yet this perspective is not just humbling, it is profoundly empowering. We are not just living in the universe, we are the universe become conscious. The iron in our blood was forged in a supernova explosion that occurred long before our sun was born. The calcium in our bones was fused in the heart of a giant star. We are stardust that has learned to contemplate the stars. This cosmic connection suggests that our ability to understand the cosmos is not an accidental byproduct, but a fundamental feature of an evolving reality. The rarity of this intelligence cannot be overstated. The chain of events required to go from a sterile planet to a technological civilization is unimaginably long and fragile. It required the right kind of star, a stable planetary orbit, the emergence of simple life, and billions of years of evolutionary stability to eventually produce a brain complex enough to grasp abstract concepts like quantum mechanics and cosmic inflation. The fact that we are here at all against such staggering odds suggests that our role carries a corresponding weight. With this awareness comes a profound responsibility, a form of cosmic stewardship. Philosopher Nick Bostrom forces us to confront the long-term future, highlighting the concept of existential risk. These are threats that could permanently extinguish humanity's potential, from asteroid impacts and pandemics to the unforeseen dangers of advanced artificial intelligence. In a universe that may be largely silent, the value of a single spark of consciousness becomes incalculable. Our duty, therefore, may be to ensure that this spark does not flicker out but endures and grows. Imagine a future where humanity has spread through the galaxy, establishing outposts around other stars. Our descendants would no longer be a single-world species, but a cosmic civilization carrying the story of life across the void. This is not just science fiction, it is a tangible possibility that hinges on the choices we make today. The ethical implications of our cosmic context are immense. Does knowing we are the universe's awareness give our lives deeper meaning? It shifts the search for purpose from something granted to us to something we actively create. Our meaning is found in the questions we ask, the beauty we create, and the legacy of knowledge and compassion we leave for the future. The cosmos gave us life and mind, and in return we give it a voice. Our most sacred duty in this vast, silent expanse may be simply to see it, to understand it, and to ensure that the light of consciousness continues to shine. Our journey has taken us from the first quantum flicker of existence to the silent, stretching fate of everything. We have seen a cosmos that may have no true beginning or end, a dynamic arena where dark energy might be fading or growing, forever altering the final chapter. The delicate fine-tuning of every physical constant points toward either an infinite multiverse or a deeper, hidden logic waiting to be found. And through it all, our own consciousness emerges not as a passive observer, but as an active participant in a reality that may be fundamentally computational, a cosmic computation of breathtaking complexity. These are not just abstract ideas for physicists to ponder. They are the very framework for our search for meaning, reshaping our understanding of our place in the grand scheme. The astronomer Carl Sagan once reflected that we are a way for the cosmos to know itself. In these new interpretations of cosmic evolution, that statement takes on a profound new weight. We are not just living in the universe, we are the universe becoming aware of its own story, from its fiery birth to its ultimate destiny. How does this perspective change the way you see your own life, your connection to the stars, and the fragile beauty of our pale blue dot? We would love to hear your reflections in the comments below. If these mysteries beyond our horizons have sparked your curiosity, subscribe for more journeys to the edge of understanding. And always, no matter what, never stop looking up.